The first image from the International Square Kilometre Array Observatory's telescope in Australia, SKA Low, has been released, marking a significant milestone in its quest to reveal an unparalleled view of our universe. Lead commissioning scientist at the SKA Low, Dr. George Heald, is beaming in to take us on a deep dive on this episode of Talkin' Science. Dr. Heald, welcome to Talkin' Science. This incredible image is just the test, the teaser of what's to come.
That's right. Yeah, thank you very much for having me. I'm glad to talk with you today about this first image. So this is just the first glimpse, indeed, of what we're going to see with the full telescope when it's available. So with this first image, we're able to take just a quick first look at this part of the sky where we see can already see 85 galaxies shining in radio waves. Eventually, when we have the full telescope built, we're expecting to be able to see up to 600,000 galaxies in just the same piece of sky. So really, it's a first taste of what's to come.
It is very exciting. In the image, we're seeing about 25 square degrees of the sky. The analogy I used from the press conference, the press release earlier in the week, was that that's equivalent to 100 full moons, which sounds large, but it kind of isn't.
It's in a way, it's just a small piece of the full sky that we'll be able to observe with the telescope. But really, when it comes to the size of the universe that we're able to study, it's huge. So we have this is a very wide field telescope, which enables us to survey the universe very quickly. And one thing that we're looking forward to is utilizing the depth component of what we're seeing in that small piece of sky. So it's not just the dimensions that you see on the sky, but more the depth. And in fact, looking back in time. As we look deeper in the universe, we're looking back further in time. And this telescope is really designed to look back, right back to the beginning of the universe almost, the time when the first stars and galaxies were starting to light up, change the conditions of the universe around them. And that's the part of the universe and everything since that we're really aiming to study with this telescope.
What difference will another 130,000 antennas make to these observations?
It'll make a big difference. There's two main things that it will change. First, we'll be able to peer back to see much fainter objects. Fainter either because they're naturally fainter, there's less stuff going on in those objects, or because they're more distant, and that makes them fainter. So the most distant objects in the universe will just be faint because they're so far away. But the other thing that the increase in number of antennas will do for us is will give us a sharper view of the universe as well. So all of those objects that we can see with the telescope, again, in this small piece of sky, we'll see eventually up to 600,000 galaxies. We'll be able to see a sharper view of those galaxies and be able to understand what's happening inside them at a higher level of detail than we can currently see.
And the detail here is incredible. I can't believe that we're going to say, as you said, we're going from around 80 galaxies in the frame to 600,000. And it's not necessarily about seeing wider, it's seeing behind those bright galaxies. Yeah,
that's right. And so, ultimately, what we're looking for here is to build a telescope which not only probes back to the early times in the universe, but is also a general purpose observatory that lets us probe a range of different physical phenomena in the universe. So we are building a long-term observatory that we will be running for decades. And one of the great things about new telescopes like this, which push into new regimes of sensitivity and sharpness of view, is that we actually don't know which questions this telescope will be most effective at answering. We know what we're designing it for, but surely this telescope is so powerful that it will teach us new questions and then the answers to those questions as well, which is why we're building a telescope which is quite flexible and allows us to do many different things, so that as we learn what the questions are that we should be asking, we can also find the answers to them.
It's kind of the first step in understanding anything, isn't it? Is figuring out those questions that we don't know that we need to be asking right now.
Indeed. And as I said, it's actually a feature of these new powerful telescopes. This has happened before, that a telescope will be built for a particular purpose, but then it winds up finding something that was entirely unexpected. And we very much expect the unexpected with this telescope.
And I'm reminded of the recent loss of the Arecibo radio telescope in South America. Obviously, SKA hasn't been built to replace that. It would have been nice to be working alongside it. But having lost that, but also having already sort of been walking a little bit with SKA, and now it's coming online, the chasm of information that we're missing out on is soon to be filled.
Yeah, so this telescope is really again very flexible, and the comparison to Arecibo is interesting. One of the things that has driven the design of SKA Low is that it's a very large number of small antennas spread out over a wide area, and the reason that we do that is because we can utilize the power of high performance computing to combine the signals from all of those individual antennas in a sophisticated way, in order to simulate a single telescope which is as large as the largest separation between the antennas, which in this case is 74 kilometers. So the furthest antennas in SK Low will be 74 kilometers apart from each other. And by combining all of their signals in the right way, we have a virtual telescope which is 74 kilometers across. So it's as if you had an Arecibo dish sitting in a crater 74 kilometers across, which obviously is completely impractical to build. So that's why we lean so heavily on the power of supercomputing for our needs.
But my biggest question is Bond's supervillain going to be able to use the SKA Low to hatch their evil plans?
I do look forward to the first action movie taking place with SK Low.
It's got to involve Tom Cruise running or something like that.
Let him know my email address.
I love it. This is interesting as well, is that it's not just this one telescope in Western Australia. It is also the MID telescope in South Africa. How are the two going to work together?
Yeah, that's a great question. So indeed, the SK Observatory is building two telescopes, as you say. SK Low is being built here on Wadjuri Yamaji country in Western Australia. SK Mid is our sister telescope, which is being built in South Africa, in the Karoo. It operates at significantly higher radio frequencies. And what that means is that the design of the telescope is fundamentally different from SK Low. It has the same design feature that we have a large number of small dishes in the case of MID, which are combined together with computing in order to simulate a large telescope as big as the largest separation between them. But rather than being fixed antennas like in SK Low, they're instead what you might consider more traditional dish antennas, which can point around in different places physically by moving the antenna. And that comes with pros and cons. They're more complicated mechanically, obviously, than just a fixed Christmas tree looking device on the ground as we have here in Australia. But they're also more sensitive, and you can pack a lot of sensitive electronics on them to look deeply into the universe. So they will work together, SK Low and SK Mid will work together by combining their forces to answer science questions that use the full range of frequencies that the telescopes can observe together. And also by giving a different view of the sky. So they can see, because they're in different locations on the globe, they can see different parts of the sky at the same time. So if they're following up, for example, something which flashes on and off in the sky, then we have an increased chance that one of the telescopes can observe it.
And how do they? So I've always wondered, a radio telescope, and we see images. How does that come about? How do we go from listening to seeing?
Yeah, so that's also a very good question. So what we look at with radio telescopes, or what we observe with radio telescopes, is radio waves from naturally occurring radio waves from objects in the sky. We don't listen to them. It's not like the movie Contact, where we plug in a pair of headphones and listen to what's happening in the sky. That doesn't really happen in real life. What we really do is we have again supercomputers, which take the signals recorded by each of the antennas, convert them into digital signals, and then process them as data streams. So what we do to generate images is we have. I keep on mentioning supercomputing. Supercomputing is really at the heart of both of these telescopes, and more so, in a way, more so for SK low than for SK mid. We use the computing not just to form the virtual large telescope from all of the small pieces, but we then also use further supercomputing to generate an image from the signals that are received. So it's done with the power of a technique called the Fourier transform, which is just a mathematical technique that allows us to generate an image that we could simulates what we would see if we had radio eyes, basically.
And it's been a long time coming. The SKA has taken many years to pull together. Coordinating two countries, two governments, certainly not an easy task, but it has been done. Can I assume that the rewards are going to be worth the wait and indeed even the pain?
Well, I think the first signs are that the telescopes are going to perform as we hoped. This indeed is a long-running project. Radio astronomers in general, have been hoping for this project for decades now. At this point, it's a very complicated project. It has taken a long time to put it together, and indeed the project is a very large international project, which is run by 16 member countries, actually. So we're building telescopes in two countries, but this is very much an international project. So it's, as I said, an international organization of 16 countries, which is building both of these telescopes, one in Australia, one in South Africa.
And that's a point not to be lost as well. Obviously, two countries are hosting these telescopes, but it's not just these two countries. Thank you for pointing that out, that yes, there are indeed 16 member nations to this, sharing data, sharing time, sharing people and resources as well, to really further our understanding of what's happening out there closer to the Big Bang.
Indeed. Yeah, and that's why the large community that has been waiting for this telescope for decades is spread out all across the globe. So really, all parts of the international astronomy community have been working towards this telescope for a very long time.
Fantastic. Dr. Hield, thanks for your time and this deep dive into SKA low. Looking forward to many more of these images and these data streams coming out in the very near future.
Thank you, Matt. Great to talk with you.
Daily science and space stories with an Aussie flair. Like, follow and subscribe for more. Become a member at thetrek.zone/support to go behind the scenes and get early access. This is Trekzone's Talkin' Science.